Hello students, to the sixth lecture of our course Wave Optics. Today we will going to discuss about the superposition of waves, the concept of superposition. So we have lecture number 6 today. So our topic today is very interesting, and that is superposition of waves. As the name suggests, what I try to say is simply that if we have two waves, it can be different, it can be same, frequency can be different, amplitude can be different. If I superimpose these two waves, say psi 1 and psi 2, then what will we get here as a sum? So let me write down the 3D wave equation once again. And we have del square psi is equal to 1 divided by v square del 2 psi del t square. V is a velocity. I am just writing for a general wave, not for electromagnetic wave. Now, if psi 1, psi 2, psi 3 and psi n are the solution of this wave, then the general solution I can write as, these are the individual solution of this wave, then the general solution we can write simply psi is equal to a linear combination of this wave. J can goes from 1 to n. So that is essentially, this is essentially is the principle of superposition. This is essentially the principle of superposition. So now we'll try to understand that if two wave, because this kind of situation we always have when we deal with optics, especially when the optics two light are interfere with each other. Two light if I combine two light, for example, with same frequency, then essentially we superimpose these two waves. That means superposition principle we apply on them. And then what should be the situation, how we deal with this situation, let us do in today's class. So suppose we have one wave E1, and that is say E10, amplitude is E1 is E10, and then it is a propagating wave. Let us consider say along x direction. So I write this is kx1 minus omega t plus a phase phi. So these are the same frequency. Another wave I can write E2. I write E2, and in this is 20 cos, and I write kx2. I am just try to find the superposition of these two propagating wave at same frequency two different point x1 and x2. This is phi 1 and this is phi 2. So this I can write. So this quantity kx1 plus phi, I write this quantity as alpha 1, and kx2, so sorry, this is phi 1 plus phi 2, the phase of the another wave, I write alpha 2. If I do that, then I have to wave like E1 is equal to E10 cos alpha 1 minus omega t, and E2 is E20 cos alpha 2 minus omega t. So the frequency of the two waves are same. The difference is this. So two different point I am trying to find out that what is the superposition so of these two waves. So using the linear superposition principle, if I have the superposition, then ER, that is the superposition of these two waves, is E1 plus E2. That is called the linear superposition. And E1 and E2 will be represented by the form we have. So essentially ER will be E10 cos of alpha 1 minus omega t plus E20 cos of alpha 2 minus omega t. Well, I can expand this cos, and if I do, I have E10, then cos A minus B, so it is cos A cos B plus sin A sin B. So I have other expression which is cos A cos B plus sin A sin B. And then what we do, we just, let me write ER here, we just take these sine and cosine component. So sine omega t, if I take common, then I'm going to get a set here like E10, then sine alpha 1 plus E20. Here we have sine, one sine is here sitting. Okay, here we have 1, here we have 2, and then we have sine alpha 1, and then E20 I should have sine alpha 2. Plus similarly, if I take cos omega t, this term common, we're going to get E10 and then cos alpha 1 plus E20 cos alpha 2. Now let us consider that this entire term I write E0 cos alpha, which is E10 cos alpha 1 plus E20 cos alpha 2, and E0 sin alpha, we write this term, which is E10 sin alpha 1 plus E20 sin alpha 2. Straightforward algebraic calculation I am doing, nothing special. And then if I want to find out what is the magnitude we have for E0, if I want to find out what is E0 and alpha in terms of this, that we can also find. And you can see that by the way, this term, this is the time independent part that I am taking aside, and I can find out E0 square. That is what I do in order to, so I make a square and add, and if I do that, then I'll go to get E0, because cos square alpha plus sin square alpha should be 1. And in the right hand side, if I do the same thing, it is easy to show that it is nothing but E10 square plus E20 square plus 2 of E10 E20 and cos of, it should be the sine cos combination, and it should be cos alpha 2 minus alpha 1. And if I want to find out what is alpha, then that we also can find that tan alpha is equal to E10 sin alpha 1 plus E20, just make it divide this divided by this, if I do sin alpha 2 whole divided by E10 cos alpha 1 plus E20 cos alpha 2. So I can also figure out what is my E0 and tan alpha, so that I can find this value E0 and tan alpha using the known value E10, E20 and etc. And if I put this back here, so the point is I can have the resultant wave as E0 cos of omega t minus alpha. So the resultant wave, the initial two waves should have was having the form of cos, and the final wave one can also have the form of cos. Important thing is the frequency will remain same. If I add these two, the frequency will remain same, but there might be something here that is sitting, and that is a phase term. So there will be something related to the phase. So the resultant amplitude, whatever the resultant amplitude we have, is this for the superposition of these two waves. So let us now check one by one. So this is the resultant amplitude one can have. This resultant amplitude is now having E10, E20, that is the individual amplitude of these two waves, and also a term that is sitting here, which is related to the individual phase of these two waves. Alpha 1 and alpha 2 are the phase of these two waves that we had earlier. So resultant amplitude, if I write alpha 2 minus alpha 1, this delta, that is the phase mismatch between these two waves, the relative phase difference, then the resultant amplitude I can write down as E0 square is equal to E10 square plus E20 square plus 2E10 E20 and cos of delta, where delta is alpha 2 minus alpha 1. Now depending on the value of the delta, one can have this value different. That is the interesting part. So delta again, which is alpha 2 minus alpha 1, so let me write down explicitly in terms of known value. So delta, what we have here is alpha 2 minus alpha 1. So this is essentially k x2 minus x1 plus phi 2 minus phi 1. So the delta, which is the relative phase between these two waves that are superimposing, is related to this quantity. So if I have x1, x2 or phi 1, phi 2, this value multiplied by k in such a way that delta is 2 pi into m, then what happened, that I am going to get E0 square a value like E10 plus E20 whole square of that. Okay, so that is the value one can have when the value of the relative phase is simply 2 pi by m. If m is 0, then also we have cos delta value. In simple case, let us put m equal to 0. So if delta is 0, that means the relative phase between the two wave is 0, then we have this quantity, which is the interfering term. This is a cross term, that is basically the interference of these two different waves. This term goes maximum. And when we have delta equal to 0, this term is maximum, and then delta equal to 0, cos delta become 1, and we have E1 square plus E2 square plus 2 E10 E2. So that means it is essentially E10 plus E20 whole square of that. On the other hand, this is when delta equal to 2 pi, when 2 pi n, when delta is equal to say 2m plus 1 and pi, then what happened? Then this term cos delta will be, in this case what happened, let me write down, cos delta will have plus 1 value. In this case what happened, the cos delta will have minus 1 value. M here is integer, 0, 1, 2 and so on. So what happened in that case, E0 square, that is the resultant amplitude, will simply become E10 minus E20 square of that. So that means based on the value of the relative phase, we can have two waves when they are interfere or they are superimposed. then two wave sometimes can get a higher value, which is this one, and can also sometimes get a lower value given by this. So these two value differs because of the value of the delta. Based on the value of the delta, we can have this. So inside the delta, what we have two phases and this k x2 minus x1 term. So if, say, forget about this phase term, let us take these two phases same. So two wave that is coming out from a point have same phase. So if phi 1 is equal to phi 2, then delta is simply defined by k multiplied by x2 minus x1. So k multiplied by x2 minus x1 is essentially 2 pi divided by lambda x2 minus x1, or I can write, so this, this is in free space, so if I write in a medium, it should be 2 pi divided by lambda naught. Lambda naught is the wavelength of the lambda naught is the wavelength of the light or the electromagnetic wave in free space. If it is in a medium, then I need to multiply a term n, which is refractive index, and then x2 minus x1. So this term actually n multiplied by x2 minus x1, this term is essentially called optical path or optical path difference in this case, because we have x2 minus x1. So this is in general called path difference. So if two waves is moving in such a way, there is a path difference between these two that one can calculate by this. So two waves are moving and they are reaching to some point, and if there is a path difference between these two, that path difference can lead to a phase difference between these. And when, so let me try to visualize these things, because that we are going to use. So suppose we have two sources like this, one is red and another is blue. So I will going to have a wave that is emitting from this, and it is moving like this and reaching to a point, say P here. So another wave that is also moving and going to that point, same point P here. Now at this point, at P point, these two waves are superimposed to each other. So if I write in our previous notation, the field that we are having here is, this is for E1 and this is E2, and this is my ER, which is E1 plus E2. So if there is a path difference, because they are moving to different length, so what happened that when we have try to find out what is the resultant wave here, that is the superposition of these two, we find that the relative phase play an important role, and this relative phase delta is coming through the path difference between these two when we consider the wavelength of these two are same. So lambda or wavelength or the frequency is same for E1 and E2. So interference is solely coming through the relative phase between these two, phi 2, phi 1, or the path difference that is create a relative phase with this. We already considered that there is no initial phase difference between these two, only the phase difference coming through the path difference, and we get the interference pattern there. And this interference pattern essentially gives you either a wave that is more amplitude with the initial combine of the two wave, or sometimes it is less. So if I try to show this figure, try to understand this figure simply. So this is, say, one wave. So this is my E1, and I can have another wave. With different amplitude. I don't know, maybe we take the same amplitude. No, we take different amplitude, because in E1 we take this amplitude was E10, and for E2 let us take another amplitude but the same frequency, maybe a less amplitude, and this is my E20. And if I add these two, if these two are in phase over the time I am propagating, if these two are in phase, then I'm going to get a resultant wave something like this. And in this case, if it is the resultant is E0, so this is my ER, which is E1 plus E2. This is my E2 that is vibrating, and my resultant amplitude here is E10 plus E20 square of that, when delta is 0. Another case we can also consider, and if I show that pictorially, and so that this this schematic figure, I have the same wave and this is my E1. This magnitude is E10, and I have another wave with lesser amount of magnitude but same frequency, and this value is E20, and this is my E2 wave. And if I add these two, I'm going to get a resultant wave with less amplitude than previous one. This is my ER, which is E1 plus E2, and this value is my E0, and here E0 square is equal to E10 minus E20 square of that. In this case, my delta is the phase. Okay, here I am making a mistake in this figure, because the phase difference between these two, they are not in the same phase, and this phase, suppose the value is such that this phase is pi. The phase difference between these two is pi. If that is the case, then what happened, that we will going to get a resultant wave with less amplitude. Note that if E1 is equal to E2, in this case the resultant amplitude vanishes. That means when we have two waves, and if their phase relationship is such that they interfere in a destructive manner, there is a possibility that even you add two waves, they will cancel out each other and we are going to get zero intensity. On the other hand, if we add two light, there is a possibility that we are going to get more higher intensity light. At least the distribution will be high in one, and we will get a wave with high value of amplitude, peak amplitude, if they are in phase. So superposition of these two waves we discussed today, and we understand that when two waves are superimposed with each other, then what happened, that they can also leads to a higher amount of magnitude. The resultant wave that is coming out through the mixture of these two waves, the superposition of these two waves, can have higher magnitude or they can have a lower magnitude as well. And this entirely depends on the relative phase between these two. So interference, the concept of the interference will come through this picture that we discussed today, that if I add these two waves, then what happened, if they are in phase, then they are going to interact in a constructive manner and we are going to get a constructive interference. And if they are out of phase, then their superposition leads to something called the destructive interference, and we are not going to get any light of that, even though we are signing the screen with two light. So that thing we are going to discuss in detail in our future classes. But the concept of the superposition, the concept of the propagating wave, and how one can deal with this superposition mathematically, that we described today. So with that note, maybe I would like to conclude. In the next class, what we do, that we will going to discuss about how the superposition of wave can be treated in a complex notation. And when we do in a complex notation, we find that things will be little bit simpler. We can understand that instead of adding two waves, if I add more and more waves, say 3, 4, 5 waves or infinite number of waves, how to deal with this addition of wave in terms of superposition principle. So with that note, let me conclude today's class. Thank you very much for your attention and see you in the next class.